This video sums up the properties of the different states of matter. Here's a jar of gas molecules, and they're shaped funny because that's trying to depict their movement. But anyway, they're moving around and they're colliding with each other. It's mostly empty space, and the particles are independent. On the microscopic level, that means that their kinetic energy is greater than their attractive force because they're at a high enough temperature. On a macroscopic level, this means that they will expand or compress to fit any container. Now, this is a property known as fluidity. Also, we know that their density is low, like 1 gram per liter for air at room temperature. So here we've got our solid, and notice it's very rigid. The particles are close together. They can vibrate, but not exchange position. And the hotter it is, the faster they'll vibrate. But solids exist at a temperature that's low enough that the kinetic energy of the particles is lower than the attractive force, as opposed to gases where the kinetic energy of the particles is greater than the attractive force. In terms of their macroscopic properties, their shape is fixed. You can't change the shape of a solid. Well, maybe if it's a metal you can, but generally it's not going to just expand to fit any size container. So it's got a fixed shape and size, right? And also a very high density, right? So the density of a solid is greater than 1,000 times the density of a gas. In fact, because the particles are touching and the density is high, solid is an example of what is called a condensed phase. Liquids represent the intermediate between gases and solids. On the micro level, the particles are touching their neighbors, but they're also allowed to exchange position. Now, the particles touching means that it is a condensed phase, just like a solid. But the fact that the particles are allowed to change position, what does that mean on the macro level? So, because the particles are touching and it's a condensed phase, that means it's going to have a high density, right? In other words, the density of the liquid is about equal to 1,000 times the density of a gas, right? That's what it means to be a condensed phase. But since the particles are allowed to exchange position, well, a liquid has something in common with a gas in that it is fluid. Now, on the macro level, being fluid means you take the shape of your container. Liquids, however, are not compressible the way gases are. Right, so at the macro level, they're not compressible. That's because at the micro level, the particles are already touching their neighbors. One last thing to say about liquids on the micro level, and that is the relationship between kinetic energy and attractive force. We've seen that liquids are kind of intermediate between gases and solids. In gases, the kinetic energy is higher than the attractive force. In solids, the kinetic energy is lower than the attractive force. So being intermediate means the kinetic energy is in balance with the attractive force, if you will. Right? So liquids really do share some properties with gases, being fluid, and some properties with solids, being condensed. So look at this liquid here. All the particles are colliding and exchanging positions. Look at this one. It had enough energy to escape out of the liquid phase. That's called evaporation. as I increase the temperature, even though we are below the boiling point, the amount of evaporation increases because now you have a higher percentage of molecules that have enough energy to escape. Right, so here's a static picture. Down here, you've got your molecules in the liquid phase. At the surface, some of those molecules have enough energy to escape into the gas phase. Okay, so that means that the total pressure there equals the pressure due to the atmosphere plus the vapor pressure, right? And that's the pressure exerted by those molecules that evaporated. And the vapor pressure increases with temperature. Fun fact, at the boiling temperature, or the boiling point, the vapor pressure is equal to the atmospheric pressure, and all of the liquid is now free to escape into the gas phase. So here's a graph showing how the vapor pressure increases exponentially with temperature. And then if you have atmospheric pressure right here, well, you can extrapolate over and find the boiling temperature. Vapor pressure curves look different depending on what your substance is. So it would be possible to have a substance that has a higher vapor pressure at virtually every temperature, and it would be possible to have other substances that have lower vapor pressures at every temperature. Notice they will have different boiling points. The substance with a higher vapor pressure has a lower boiling point. The substance with the lower vapor pressure has a higher boiling point. So when you have a high vapor pressure, that means high volatility. And that's just a measure of the tendency to evaporate. Having a low vapor pressure, that means low volatility. Have you guys ever seen dry ice? Dry ice is the process where a substance spontaneously goes from a solid state to the gas state. Now think about it. With ice, if you heat it up, it goes through the liquid. Well, some substances like dry ice go directly from solid to gas, and that's called sublimation. So you can see here in this video, this person takes a little chunk of dry ice and drops it into a flask full of water. And then, if you look at it, at the very bottom of the water, you can see gas forming. But the dry ice isn't melting. It's just turning straight to gas. That's sublimation. And we say the more volatile a substance is, the faster it sublimates. In this case, we've got CO2 solid, that's the dry ice, becoming CO2 gas. And look at that. Imagine serving cocktails with dry ice for Halloween. Anyway, if you want to measure the vapor pressure of a substance, you use a manometer. This is also related to how you measure blood pressure. That's a sphygmomanometer. So anyway, there's two kinds of manometers. There's a closed end and an open-ended manometer. So in the closed end one, on the left here, the pressure in the gas is just equal to the height difference, right? And you have this substance inside here is mercury, liquid, right? So it takes quite a bit of pressure to move the mercury. right? And in fact, you can read the pressure directly in millimeters of mercury, or torr, right? Now, with an open-ended manometer, you have something else happening here. This is atmospheric pressure. So, in this picture here, the gas is exerting more pressure than the atmosphere, right? Because it's pushed the mercury lower, right? The atmosphere is not pushing as hard because the mercury on the atmosphere side is higher. Okay, so here we say the pressure in the gas is equal to the atmospheric pressure plus the height, right? Now, if, right, and that's the height in millimeters, and if you change that to millimeters of mercury, then this works. If it was higher on the atmosphere side, then we could say the pressure of the gas is equal to the atmospheric pressure minus the height, right? So then we'd write P gas equals PATM minus H. And again, this works if you express your pressure in millimeters of mercury and measure your height in millimeters. Now let's do an exercise. So the exercise is to find the pressure of the gas if the atmospheric pressure is equal to 631 millimeters of mercury and the height is 57 millimeters. That's higher on the open end. Pause your video and work it out. Now here's how to solve it. The pressure of the gas equals the pressure of the atmosphere plus the height. So that's 631 mmHg plus 57 mmHg. And if I punch that into the calculator, I get 688 millimeters of mercury. And if you divide that by 760, you get the pressure in atmospheres, which is 0.905. Another cool property of liquids is surface tension. You see these drops of mercury? That's liquid metal. Well, they're round. Why are they round? Well, consider the mercury atoms. They're attracted to all of their neighbors. So a mercury atom in the center is attracted to one below and to the ones on the sides and to the ones at the top. That molecule feels no net force. However, consider a molecule that is on the outside. Like this molecule in the upper right-hand corner, it's being pulled in that direction, and that direction, and that direction, and that direction, but it's not being pulled up and to the right at all. The net force it feels is pulling it inward, right? And so you could define surface tension as attractive force between the molecules or the atoms makes the particles at the surface experience a net pull inward. And this creates a skin on the surface of a liquid. Have you ever seen those bugs that can walk on water? It's because their weight is less than the surface tension. So this is also the reason why droplets of water are spherical. Another property of liquids is capillary action. A capillary is a thin tube. So capillary action is when you take a thin tube and you stick it into a droplet of liquid, and the liquid gets pulled up into that tube. In the healthcare profession, you'll see this with blood. Blood does this. Capillary action happens because the attractive force between the liquid particles and the material of the capillary tube is stronger than the attraction between the liquid particles and other liquid particles. Now, consider two tubes. We've got mercury and we've got water. Now look at the shape of the meniscus. On mercury, it's convex. That means that the attraction between the mercury atoms is stronger than the attraction between mercury atoms and glass. That means for mercury, we will see no capillary action. However, look at the meniscus on water. That is concave. So because of that concave surface, we can say that the attractive force between the water and the glass is stronger than the attractive force between water molecules and other water molecules. When you get that into a thin enough tube, there are so many more interactions between glass and water than between water and water, that you see capillary action.